isn't flashing, but okay, I'm ready to start, I think, and hopefully all goes okay. So you can still hear me and see what's going on here? Okay, now I'm going to start for real. All right, so the notes that I sent you guys, I'm just going to go through those quickly. So our trigonometric identities, this first page, as I wrote, we already know these in the sense of when I talked about cosine, sine, and tangent, we talked about how secant, cosecant, and cotangent are just their reciprocals, and hence that's why it's 1 divided by cosine or 1 divided by sine. Just like on the other side, if secant's the reciprocal of cosine, then cosine's the reciprocal of secant. So that's why all of these are 1 divided by their reciprocal function. So these we kind of already knew already, just in the sense of x divided by y, or y divided by x, or r over x versus x over r, that kind of thing. The two new ones that, again, we also knew in terms of x, y, and r are that tangent is sine over cosine, because as we know, tangent is y over x, or in other words, y over r divided by x over r. So let me try this tablet for the first time. It's a little different from my other tablet. So again, sine is y over r, cosine is x over r. Obviously the r's just cancel, and that leaves us with just y over x. So we already knew that tangent was y over x, so now we can just think of tangent in terms of sine divided by cosine. So that's an important identity to remember. Similarly, cotangent is just cosine over sine, which is x over r divided by y over r, and that just simplifies to x over y. So these 8 identities on this screen are going to be important when we do our proof writing, because we'll be able to use them to swap out certain terms with other equivalent terms, and that's what makes them identities. Okay. And again, I don't have the chat screen showing. So again, just make sure you chat if you have a question, or undo your mic, so that I know to look out for that. Okay. So now I'm going to go to the next page. The next identity is called the Pythagorean identity. This page was just to develop that. So all I did was I put a right triangle in the circle. We already know the Pythagorean theorem formula. Based on the labels of this triangle are x squared plus y squared equals r squared. So using the definitions of what cosine and sine are as x over r and y over r, I just rewrote those by multiplying r on both sides, so that now we know that x is r cosine theta and y is r sine theta in green, so that then in the Pythagorean theorem formula, we can replace x and y with those green terms, and then squaring and simplifying means after I divide everything by r, we're left with this red identity. Cosine squared plus sine squared equals 1. That's a huge trigonometric identity that we're going to use a lot. And that's called the Pythagorean identity, obviously because it's based on the Pythagorean theorem formula. Okay, so in addition to the 8 trig identities on this previous page, the Pythagorean identity is the next one that you would add to your list of identities. Okay, cosine squared plus sine squared is always equal to 1. So on this next page, all I did was verify using an example of our angle 2 pi over 3. I could have used any angle. Any angle you choose when you plug it into cosine squared plus sine squared and you do the simplification, it should always equal 1. Okay, as long as your angle is the same when you plug it in, then squaring both the cosine and sine and then adding would give you 1. So this page was just to verify that it works. So nothing hugely important on this page other than verifying the identity. On the next page, I derived 2 additional Pythagorean identities by taking the Pythagorean identity that I have in black on both sides, and for each one, I divided by cosine squared on the left side of the screen and sine squared on the right side of the screen. I chopped up the fractions, okay, on the second line, and then in blue, cosine squared over cosine squared is just 1. Sine squared over cosine squared is tangent squared, because we know that sine over cosine is tangent. We also know that sine to any power over cosine to that same power would be tangent to that same power. So sine squared over cosine squared is tangent squared, and 1 over cosine squared is the reciprocal identity for secant squared. So by dividing everything by cosine squared, I developed this new Pythagorean identity that I boxed here in blue. And then similarly, if we divide it by sine squared, simplifying everything on this side and using identities, cosine squared over sine squared is cotangent squared using the quotient identity. Sine squared over sine squared is obviously just 1, and 1 over sine squared is cosecant squared. Okay, so that's how I got this third Pythagorean identity. So that's 3 Pythagorean identities altogether. The primary one, though, is the one up here in black. Cosine squared plus sine squared equals 1. Okay, that's the one that if you Google Pythagorean identity, trigonometric Pythagorean identity, that's the one that you'll probably find the hit for. But these other 2 obviously are also Pythagorean identities that are derived from that first one. Okay, just checking the camera real quick. Or is everyone still okay? You can still hear me and everything? Cool. All right. Something's flashing at me. Okay. So, back to the notes. So, here's the first proof that I did. Now, the text that I provide is that in proof writing, our goal is to prove that the left side of what I give us is equal to the right side. So in other words, you have to prove that A equals B. Okay, I wrote in here that that means we're not trying to prove B equals A. So you can't switch the order. Okay, in pure mathematical sense, whatever I give you as the direction of the proof, that's the way we have to do it. So my task is to show that 1 plus tangent squared, if I rewrite it however many times I need to with equivalent expressions, I will end up with secant squared, which is what I would be trying to prove. So what you do is you start with the left-hand side. So I started with 1 plus tangent squared on the left. And then on the right side, I have to now start changing the way it looks while keeping the identity, meaning keeping the equivalence. So I kept the 1, but tangent squared I replaced with sine squared over cosine squared using that quotient identity. Then the 1 I replaced with cosine squared over cosine squared because I wanted to merge these two things, and the only way I'd be able to do that is to get a common denominator. So if the fraction has cosine squared as its denominator, I rewrote 1 as a fraction with cosine squared as its denominator. So that takes me to line 2. Line 3, what I did was now that I have the same denominator, I was able to add the two fractions, which means adding the numerators together and keeping the denominator cosine squared. Okay, just like we would if I had something like 1/7 plus 2/7, that would be 1 plus 2 over 7. Same kind of idea. Once I had that single fraction now, that numerator is just our Pythagorean identity. Cosine squared plus sine squared is equal to 1. So what I did to get to the next line is I just replaced the numerator with a 1 because I knew that Pythagorean identity is equivalence. And then once I had 1 over cosine squared, that is just the definition of secant squared using the reciprocal identity. And then once I had secant squared, that was exactly what I was trying to show on the right-hand side. So my proof is done, and I write QED, which on the left-hand side is Latin, which stands for basically, which was to be proven. So this right here is a proof for the black thing that I started us with, proving that 1 plus tangent squared equals secant squared. And again, as I put here on the side, from the earlier page on the notes, we already showed that this was one of the Pythagorean identities, but I just wanted to show a proof for how that can be showed. Okay, so this is one proof. Now, the thing with writing trigonometric proofs is there's lots of different ways you can prove things. So I was able to finish this proof in 1, 2, 3, 4, 5 lines it took me. One of you out there, if you had proven it, you may have taken 7 lines. Okay, someone else may have done it shorter than I did and could do it in 4 lines. So the best proofs are always the most efficient, compact proofs. Okay, but that doesn't mean that there aren't other variations of proofs. Okay, so one of the things that you have to get used to in developing the skill with is trying to find a way to prove something without going in too many circles. So I often have students turn in proofs to me where they have like 20 lines worth of a proof, and in lots of places what they did in one place they undid later on, and so it was just a lot of extra steps that could have been condensed. But while you're practicing with proof writing, sometimes you don't realize where you're going until you're 7 steps down the road already, and then a light bulb goes off and then you may be able to see how to finish the proof. So it's okay if your proof is longer than one of your friends or vice versa, until we get the hang of it. All right. So this was one proof. Just checking in. We still are okay. Audio still is good. Screen can be seen. Cool. Okay. So next example was proving that tangent of beta equals tangent of beta plus cotangent of beta equals secant of beta times the cosecant of beta. So again, you start with the left-hand side only, and then on the right-hand side, I need to start writing equivalent expressions that I know are true as many times as I need until I get the thing on the right-hand side that I was given. So my first step was to use quotient identities for tangent and cotangent, meaning that tangent is sine over cosine and cotangent is cosine over sine. So I swapped those in. Then to add these two fractions together, I had to get a common denominator. So with the first fraction, I multiplied top and bottom by the denominator of the other. And for the second fraction, I multiplied top and bottom by the first fraction's denominator, just as you would getting a common denominator with regular numbers. That gives me the next line here. And now that I have the common denominator of sine beta cosine beta, I added the two fractions together, which means adding the numerators and keeping the denominator the same. Again, in the numerator here, sine squared plus cosine squared is the primary Pythagorean identity, which means I can replace that with just the single one. Then once I had 1 over sine beta cosine beta, I separated that out into two fractions because in the thing that I see I'm trying to prove, I need two separate terms multiplied together. So when I have this single fraction, I realized let me split it up now into two fractions multiplied. So 1 over sine on its own times 1 over cosine. And then 1 over sine, by definition of its reciprocal identity, is cosecant, and 1 over cosine by its reciprocal identity is secant. And then cosecant times secant, when you multiply, is just the same thing as secant times cosecant. So I reordered that so it looks like the original thing I was given. And that is what I was given on the right-hand side. So then my proof is done, so I put my QED in. Okay, these steps on the side are just summarizing what I said out loud. When you write your proofs, you don't have to put the steps on the side. I'm doing that in the notes just so you all can understand what I did from line to line to get my proof. Okay, but the pink stuff really isn't needed. It's this main thing here in blue that would be needed. Yeah.
I got a question for line 4.
1, 2, 3, 4. Yeah.
My brain, I feel like I'm gonna cancel the sines and the cosines.
Okay, so don't cancel because that would be illegal because we're adding stuff in the numerator. If it was multiplying, then yeah, we'd be able to cancel. But because of that plus symbol in the numerator, that would be illegal algebra 1.
So how did you get just one, like at the end, one sine and one cosine when you're adding two sines and adding two cosines?
Well, I'm not adding two of them. It's sine squared and it's cosine squared. It's sine times
denominator.
Huh?
For line 3.
Say that one more time.
For the denominator for line 3. Because there's two sines and two cosines. But then on line 4, you end up with just one.
Right, but don't forget, in the same way... Sorry about that. Hang on. In the same way that if we had regular numbers, like 1/7 plus 2/7, I don't add the 7s together. That just stays the same, right? The 7 stays the same. It's the 1 plus the 2 that come together. But the 7 stays the same. So these denominators... Sorry, this tablet is not doing what I want it to do. These denominators stay the same, which is why this is just sine cosine. Okay?
Yeah.
Cool. Any other questions at this point from anyone else?
I do have a question.
Go ahead.
So you were just talking about doing Pythagorean identity.
Yeah.
Do I have to use Pythagorean theorem as like an identity to use, or can I use like any other equation like y equals mx plus b or something like? Is it only for Pythagorean identity? Or?
Well, so there's going to be a lot of identities I give you guys. So right now, the only ones you're really worried about are these 8 on this page. Okay, the 6 reciprocals and the 2 quotient identities. And then the 3 Pythagorean identities, meaning this red one here, which is the primary one, and then the two other ones that I boxed on this page. So right now, what is that? 8 plus 3. So that's 11 identities right now that you have that in our proofs, you can always use them to substitute where you see the identity being used. There will be other identities in the future, but for right now, these 11 are the main ones that I'm going to be using in our proofs.
And then I had another question. There's a part where you used, I think you did it on this one too. Oh, okay, never mind. I was just looking at the notes and my question was answered. All right, I'm good now.
Okay. And again, anyone else, if you have a question, just unmute your mic and just shout at me. I'll advance the page. And I'm hoping this recording is working so that I can always post this recording and you can review it back. If it doesn't work, I'll record again without everyone and post that. So here was example 3. So proof that 1 plus cosine over sine equals sine over 1 minus cosine. Again, you start with the thing you're given on the left. On the right-hand side now, I write as many times as I can to get the thing that I want on the right-hand side. So here is where a new strategy I used, different from the first two examples. So one strategy to do sometimes when you have the addition of, when you have a binomial, so adding two terms together and a single fraction, is often to use a conjugate. So if you remember conjugates with radicals like a plus root b, we multiply top and bottom by a minus root b, that kind of thing. So conjugates are used here also. So what I did was I multiplied top and bottom by the conjugate of that numerator. So if it was 1 plus cosine on the numerator, I'm multiplying top and bottom by 1 minus cosine. That's the conjugate. Once I do that, I multiplied on top by just showing everything in its factored form first. In the numerator, I then FOILed, so 1 plus cosine times 1 minus cosine, I FOILed that all out to get 1 minus cosine plus cosine minus cosine squared. In the denominator, I kept that in factored form. So a lot of you may have an impulse to distribute that sign, which you can do legally, but often in these proofs, when you multiply by a conjugate or something, something will cancel later on, which may not be as evident if you distribute everything. So I'm leaving that sign and that 1 minus cosine separate for the time being, and then later on I'll comment on that again. But now, adding like terms in the numerator, the negative cosine and the positive cosine cancel each other out, so those disappeared, leaving me with 1 minus cosine squared in the numerator, and then that denominator is still the same. Then what I have here, I put a little star. 1 minus cosine squared, if you go up here to this green recall, I have the primary Pythagorean identity first. Cosine squared plus sine squared equals 1. If I subtract cosine squared from both sides, then I'm given sine squared equals 1 minus cosine squared. That's just a reorganized version of that primary Pythagorean identity. So that now in my proof, when I have this numerator 1 minus cosine squared, up here, this purple asterisk, I know that equals sine squared. So I took that numerator and replaced it with sine squared. Then I have sine squared on top and a sine on the bottom. There's no addition or subtraction gluing these things together. So here is where I can legally cancel. So the sine squared on top and the single sign on the bottom, one cancels on top and one cancels on the bottom, which just leaves me with one on top. And the one on the bottom is gone. So now I have this final line of sine theta over cosine, 1 minus cosine theta. That is exactly what I was trying to prove. So my proof is done, so QED. Okay, so not only will using Pythagorean identities help, but look for places where a restructured version of that identity may be helpful. So when I had 1 minus cosine squared, again, your brain can think of the Pythagorean identity and just kind of subtract what you need to get what you have so that you can substitute. Questions on this page? Okay, I'll move forward. So the next thing in the notes was just a list of strategies that should be helpful when you do the proofs that I sent you. So looking for places where you see Pythagorean identities or reorganized versions of Pythagorean identities. Splitting fractions apart with multiplication or bringing them together with combining, getting a common denominator. That was done in the proofs. multiplying a fraction with the binomial on top and bottom of with the conjugate, okay, is sometimes helpful. Basic arithmetic in Algebra 1 obviously will come in handy. Substituting reciprocal or quotient identities. And then also I kind of just italicized thinking about what your goal is so that maybe what road to take. For example, on this proof, once I got to this line where I had 1 over sine beta cosine beta, this is where I kind of reminded myself from the beginning that I want two separate terms multiplied. So I kind of thought to myself, how can I get two terms from this single term? And that's why I split it up into the multiplication of two things. So that's what I mean by that last bullet point is if you get stuck or you aren't sure where to go next, sometimes it's helpful to remind yourself what you're trying to do. Okay? So if you do your proofs and you get stuck, these are pretty much the bullets that you should ask yourself, did I try and do these yet, or are they relevant? Could I do something that's on this list? Okay, so hopefully that's helpful. So let me actually go into doing the proofs that I gave you guys, okay? And again, if you have questions, shout out at me. So this first one, proving that secant squared plus cosecant squared equals secant squared times cosecant squared. So again, you always start with the left-hand side. Give me 1 second here. Okay. So you always start with the left-hand side. So I'm going to have secant squared plus cosecant squared. Oops. And now it's my task to rewrite that until I get what I need. So I don't really know right away what I need to do, but I know that I have my toolkit of the 11 identities that I have on the first couple pages of the notes. Okay, so I'm going to start there. Secant squared, I know by definition, is the reciprocal of cosine squared. So I'm going to start there and replace that first thing with 1 over cosine squared. Similarly, cosecant squared is the same as the reciprocal identity for sine squared. So I know that's equivalent to 1 over sine squared. Now that I have these two things being added, thinking about my long-term goal, I see that I have two things being multiplied. In other words, I have one single expression, whereas right now I have the addition of two expressions. So my idea to myself is let me try and fuse these two things together. And the only way I know how to do that is if these things have a common denominator. So I'm going to multiply that first fraction on top and bottom by the sine squared of x, which is the denominator of the second fraction. And then for the second fraction, I'm going to multiply top and bottom by the denominator of the first fraction. I'm just going to simplify that now. So that will give me sine squared over sine squared cosine squared. And this new tablet is definitely not mapping to my computer as well as my other one, so I'm unhappy right now. Plus cosine squared for the second one over that same denominator, sine squared cosine squared. And now that I have the common denominator, I can bring the two fractions together, which means adding the numerators, so sine squared plus cosine squared. And that denominator stays the same. At this point here, notice that numerator is my Pythagorean identity. Sine squared plus cosine squared is just equal to 1. So I'm going to change the numerator using the Pythagorean identity. My denominator is staying the same. And now again, here's where I say, well, I have a single fraction here. I want one term where I have the multiplication of two things. So I'm going to separate this fraction using multiplication. This is equivalent to 1 over sine squared times 1 over cosine squared. One over sine squared, by definition, using the reciprocal identity, is just cosecant squared. Just like 1 over cosine squared, by definition, is secant squared. And that is what I'm trying to show, just reordered. So the most elegant proof should make everything explicitly clear for whoever's reading it. So I'm just going to reorder this now. Multiplication is commutative. So I know a times b equals b times a, which means I can just reorder this. This is exactly what I was trying to prove. So I'm going to put my QED, and my proof is done. Questions?
Like, how do you know when there's like a definite finish? Like, because theoretically speaking, you can continue going on and on and on.
Yeah, I mean, I can make secant squared cosecant squared. I can keep going and change that to look like plenty of other things that are equivalent. But again, my goal is to end with secant squared cosecant squared, which is what I did. So obviously I knew on the second to last line that I was basically done, but since it didn't look 100% like what I was given, I swapped the order. Okay, so that's why I did one more line. But it's not like I want to do any more after that, because secant squared cosecant squared is what I was told to end up with. So until you end with the thing you're trying to show on the right-hand side, then you're not done. So I've had kids on quizzes and things put a QED at the end, even though their last line wasn't what they were trying to prove. So that's a little ridiculous. So you can't add the QED until you actually showed what you were asked to show. Okay, I'm going to move on to the next example. Okay, so proving that sine theta over 1 plus cosine over sine equals cosecant. All right, so there's different ways to do this. I'm going to show you the way that my brain naturally will end up showing. And then the solutions that I post, hopefully it's the same. But if you did this already, which hopefully you guys attempted these things, your proof may be different from mine. Don't forget, there are lots of different ways to prove things in different orders of things using different identities. But the goal is that we should all end up getting cosecant of theta at the end, using legal algebra, using legal definitions of identities, that kind of thing. So starting with the left-hand side, so I'm just going to rewrite that. Okay, so there's two things that my brain sees right away. I can either get a common denominator by multiplying each of these fractions on top and bottom by the denominator of the other fraction. The other thing my brain thinks of is I see a binomial here, 1 plus cosine theta, and I'm wondering if I use a conjugate, if that would help me. So those are the two different things that I would think of to try. Two separate roads that I can take, basically. I'm going to take the conjugate road, but if I used the common denominator route, that should also work. And I can always show that to you guys if you want to see that as well once I finish the first one. So again, my choice is going to be to use a conjugate on that first fraction, meaning I'm going to multiply that fraction by 1 minus cosine theta on top and bottom. And again, I don't necessarily know that it's going to work. I'm just kind of using one of the strategies that I saw that worked in a previous proof that's on that bullet pointed list I gave. So writing everything else the same way it was. So here now I'm going to, on the numerator of the first two fractions, I'm going to multiply by distributing that sign. So sine times 1 is just sine. And sine times that negative cosine is negative sine cosine. In the denominator, I'm going to FOIL. So 1 minus cosine times 1 plus cosine is 1 minus cosine theta plus cosine theta minus cosine squared of theta. Now, the whole point of using a conjugate is that when you FOIL, the middle term should cancel. So technically, when you FOIL, you really only have to think about the 1 times the 1 and the negative cosine times the positive cosine. If you're truly using conjugates, the middle terms you should know are going to cancel. So I'm going to show this here, and then in the future, if I ever use conjugates again, I probably won't show that step. I probably just would have written 1 minus cosine squared. I'm going to have my other fraction over here, cosine theta over sine theta. That doesn't change. Also notice your vertical alignment of everything should be pristine, so all the equals should be in line, just like we've used in the past with showing our work. So that's keeping good alignment in your proofs is part of writing a good proof. So now for this first term, I don't see how I confuse anything in the numerator, but in the denominator I can cancel out those middle terms. So I'm going to have sine theta minus sine theta cosine theta. So that stays the same. In the denominator, middle terms cancel, and I'm just left with 1 minus cosine squared. This other fraction is still going to be the way it was. At this point now, 1 minus cosine squared should remind you of the Pythagorean identity just written in a different order. So if I do that kind of on the side, just as side work to myself, the Pythagorean identity was cosine squared plus sine squared equals 1. So I know that if I subtract cosine squared from both sides, just like earlier, I would have that sine squared equals 1 minus cosine squared. Just like you may end up needing in a different proof, the fact that cosine squared would equal 1 minus sine squared. So we could also subtract sine squared instead, getting cosine squared equals 1 minus sine squared. But here, my denominator is 1 minus cosine squared, and that over here is just sine squared. So that's what I'm going to substitute. Making that substitution here. That second fraction is still exactly the way it's been. Haven't done anything with it yet. And now with this first fraction, notice I have a sine squared on the bottom, and on the top I have a sign with each of these terms. This is a demonstration of what I was saying earlier, where up here, when I chose to distribute this sign to both things, maybe I should have held off on doing that, because if I left it in factored form, I may more easily see that I can cancel signs now. Okay, I have a sign with all three terms, the two terms up top and the one on the bottom, which means I can cancel sign from everywhere. And again, maybe that just would have been easier to see if it was in factored form instead of me having distributed that sign. So I'm going to factor it right now. So pulling a sign away from both of those things would leave me with 1 minus cosine theta inside. So here, basically, I undid what I did up here from line 1 to line 2 when I distributed the sign. So I wish I hadn't have done that, but that's okay. I can undo it here. Or I just know by understanding arithmetic and basic math that as long as I have the sign in all three places, I could have canceled it in all three places. So I really don't need to show this, but I don't want to lose anyone, so I'm making it explicitly clear what's happening here. And now that I see that I don't have subtraction going on, I can cancel the single sign here with one of the signs on the denominator. That leaves me now with 1 minus cosine of theta over a single sine of theta plus that other fraction still. Notice both of these fractions have the same denominator, so I can add them together. I need some more room, so let me make this smaller. This is the point where hopefully you get a little excited, because if you see here, when I combine them, the negative cosine and the positive cosine are going to cancel each other. So let me first fuse the fractions together. So 1 minus cosine theta plus that cosine theta all over that common denominator of sine theta. Now the negative cosine and the positive cosine cancel each other. So I need to make more room. Once they cancel, that leaves me with 1 over sine of theta. And by definition, using our reciprocal identities, that is equivalent to the cosecant of theta. That is what I was trying to prove, so my proof is done, which means I can put my QED. So that proof was a little bit longer. Questions here?
In the beginning,
Yep.
would it have been okay to simplify the cosine over sine to cotangent?
Okay, yes, so it is true that cosine over sine equals cotangent, so that is definitely a possibility, and that just means that J would be taking a different road down her proof, which may end up being successful for her, it may end up being more confusing for her, it may end up being a shorter proof than mine, it may be a longer proof than mine, but that is valid, so you certainly could do that, yes.
I also have a question.
Yep.
Line 3, you have 1 minus cosine squared, and then you get sine squared. How did you do that?
That's where this green stuff comes in. So this stuff is equivalent to sine squared because cosine squared plus sine squared equals 1 is the Pythagorean identity. And if I subtract cosine squared from both sides, that gave me that sine squared equals 1 minus cosine squared. So I literally just took the denominator I had, and it becomes this new denominator because of this identity that's reorganized. Okay? Moving on to the next one. Starting with the left side again, secant. Sorry, let me use my blue. Now, ideally, I'd be asking you guys for suggestions, but I don't want to keep people here longer than maybe people want to be here. At any time, obviously, you can leave. But hopefully you guys tried this stuff out or have ideas here. But anyway, so secant plus tangent. I need to get cosine over 1 minus sine. I have no idea how I'm going to make that happen. Again, all I can do is just try different things that I know are true, and hopefully I get somewhere where a light bulb goes off or I see something I can do. So just like Jay on the last one asked if she could use cotangent instead of what I did, sure, try it. If it works out, great. If it doesn't, then maybe just try something else. So that's the other element of doing these proofs, which I think I put in the directions on that homework, was if you get frustrated or if you can't get somewhere, you get a roadblock, that's okay. Take a break or try something else. It doesn't come naturally. It takes a lot of practice, and you have to be okay with failing sometimes. I'm mad at myself on that previous thing that I had distributed that sign when I really didn't need to yet. But that's okay. I still got a proof that worked. So, I'm not worried about it. I still would have gotten a 5 out of 5 here if it was a standard. So don't worry about that. Just have patience with yourself is all I'm trying to say. So don't give up just because one proof was harder than another one for you, or because you got to a roadblock and couldn't get over it, that kind of thing. So again, I don't know what I'm doing here, but I know that secant and tangent, I have identities for them. The other thing I didn't put at that bullet pointed list of strategies that I'm going to say now is that sometimes it's easy to think in terms of sines and cosines instead of all of the other stuff. Since we know that we can express all of our trig ratios using sines and cosines only, sometimes it's helpful to think in terms of sines and cosines rather than the other 4 ratios, because then if you can simplify everything using the common sines and cosines, you may get to a place where you can then have something shorter or more condensed that you can always swap back with the other ratios. So here, I'm going to find a way to write secant and tangent using only sines and cosines. So secant, I know, is the reciprocal identity for cosine. So I'm going to replace that with 1 over cosine. Just like tangent, I know is sine over cosine. An idea, kind of like Jay's earlier, is someone could ask, well, why don't we use 1 over cotangent? Because that's the reciprocal of tangent. That is true. Again, if I'm sticking with my gut instinct of wanting to turn everything in terms of sines and cosines to make it easier for myself, I'm going to reject the idea of using 1 over cotangent, but that doesn't mean you can't do it, okay? So my strategy here is to get things in terms of sines and cosines only, so I don't really want to use tangent. So, sorry, I don't want to use 1 over cotangent. So tangent is sine over cosine, so I'm going to do that. I'm happy about that because notice the denominators now are the same, so I can add these two things together. And if I had written 1 over cotangent, that wouldn't have happened as nicely. Again, that doesn't mean it wouldn't have worked out using different steps though. So I'm adding the two numerators together. My denominator is still cosine of y. Now here, this sort of looks like what I want, but it's flipped, and notice instead of the subtraction, I have the addition. Here is where now the strategy of using a conjugate is going to help me out. So 1 plus sine of y, I'm going to multiply both top and bottom by its conjugate, 1 minus sine y, which should be nice because that is what I want to have in the final thing, and I want it to be in the denominator.
I got a question.
Yep.
So what if you have the conjugate of cosine of y? Would that happen? Or is it just when it have 1 plus anything else?
Yeah, so I might have had something like 1 minus cosine y or 1 plus cosine y, and maybe I would want to use that conjugate instead. That's not here, though. It's just a single cosine, so I don't really need to worry about that.
But do you need the 1 plus and minus?
I mean, here I'm multiplying by the conjugate of the numerator because I see that conjugate, 1 minus sine, in the thing I want to try and show. And I also, in my list of strategies, one of my strategies was, well, if you see a binomial, sometimes it's helpful to multiply by its conjugate. So again, I don't necessarily know that this is what I need to do, but it was an idea on that list of strategies I gave you guys, so it would be something I would want you guys to try if you didn't know what else to do. So I'm trying that out. So doing this now, I'm going to FOIL in the numerator. So 1 times 1 is just a 1. I'm going to remember that the whole point of conjugates is that the inside and outside terms of FOILing cancel. So I'm going to shortcut this by only just multiplying the 1's together and multiplying the sine and the negative sign together, giving negative sine squared of y. So here is where I'm not showing that middle step because I already know that using a conjugate means the middle terms would cancel. That doesn't mean you guys don't have to show it. You can if you want, but I'm allowing you not to, as long as you understand that the whole point of conjugates is that you can simplify those middle things, okay? So that's the numerator is multiplied together and FOILed in combining like terms. Denominator, I'm going to learn from my past mistake and keep it separate, meaning I'm not going to distribute just yet. I know that I can if I end up needing to, but if something cancels down the road, maybe it'll be easier for me to see that if I leave this stuff in its factored form rather than multiplying the cosine through. This numerator right now has a sine squared and it has a 1, so my brain dings and I think of the Pythagorean identity where both things are involved. And again, this is a reorganized Pythagorean identity. If cosine squared of theta plus sine of squared of theta equals 1, well then if I subtract sine squared from both sides, I have that cosine squared equals 1 minus sine squared, and that is my numerator right now. So 1 minus sine squared, I'm going to replace in the numerator with this cosine squared. Denominator, I'm leaving the way it was. And now that was helpful because I have cosine squared on top and a cosine on the bottom, which means I can cancel 1 from top and 1 on the bottom. leaving me with one cosine on the top, and the cosine on the bottom disappears, leaving me with 1 minus sine of y. And notice that is exactly what I was trying to prove, so my proof is done. QED.
Mr. Reddy, I have a question.
Yep.
So I'm still kind of confused on how we got the cosine squared y at the top in step
Right here.
4.
Yeah, so this was the same question that Shai was asking on the last one. This stuff here became this stuff here because I thought to myself that the Pythagorean identity here that I'm storing, cosine squared plus sine squared equals 1, if I subtract sine squared from both sides, that gives me cosine squared equals 1 minus sine squared. And if I know that's true, then I took the 1 minus sine squared and replaced it with the cosine squared.
Oh, okay. I got it now.
Yep. Anybody else? Okay. Number 4. This one actually can be done really quickly. So there is a way to prove this, obviously, in several steps, but I think I'm only going to need like 2 steps. So here, tangent squared of theta plus 4. I know that 4 is the same as 1 plus 3. That's an identity that we've known since elementary school, basically. That is an identity. 4 equals 1 plus 3. So I'm going to take this, and instead of 4, I'm going to rewrite that as a 1 plus a 3. Okay. So that is an equivalent expression. And then notice that tangent squared plus 1 is that second Pythagorean identity that we had on the earlier page of notes. If I go all the way back. Right here, in this blue box. This was one of the identities of the 11 identities that are basically like things to study right now that you should remember in your toolkit of identities. 1 plus tangent squared equals secant squared. So if I know that's true already, then in my proof that I just was doing, this tangent squared plus 1, I know is just secant squared. Plus that 3, but that's what I was trying to prove, so I'm done. Now again, if you didn't remember that secondary Pythagorean identity, that tangent squared plus 1 equals secant squared, you may have taken a much longer road to get the same thing I just got in 2 steps. And that's okay. But this is where it's nice to know identities. This is what's helpful about having identities, is that knowing that identity, I was able to finish this proof really fast. Okay, so that's the nice thing about having identities. And for the sake of the notes, I'll just put the recall up here. 1 plus tangent squared equals secant squared. Okay, so again, this was problem number 4. This one was so fast. So this is just to show you that maybe just because problem number 1 and 2 stumped you and took a long time doesn't mean that problem 4 is going to take just as long, you know? So I never make my homework assignments so that they're in any particular order of like difficulty, really. So just to kind of reiterate that you should never give up on a homework just because you had trouble with the first one, let's say, okay? Because maybe you were able to do number 4 really fast, okay? This was seconds of my time.
Just to clarify, when you're doing proofs, you don't have to write the left side again when you finish?
Yeah, thanks for asking that. So in a good proof, we should have that left side blank all the way through except for on that first line. Okay, just like I think I said with like other things we've done this year. I think when we were proving things with logarithmic expressions and properties, I think the same thing was true. Okay, we start with the thing on the left and you end with the thing on the right, and that's what you're trying to prove. So it's assumed in math all this stuff carries through all the way down, so that's why I'm not writing it. And it makes the proof easier to see visually if you don't write it, so that's why we don't do that. So yes, you should not be writing that left-hand side any longer once you write it on the first line. Okay, it means when it's blank down the road, all the way down, it means that it's what it was to start with, okay? And that's why vertical alignment and structure is really important with proofs. If I didn't have good structure, then my eyeballs wouldn't see necessarily that that left-hand side is equal to this right-hand side as cleanly, okay? All right, this last one, 2 minutes left if I keep to a normal hour-long class. So again, cosine of t plus sine t tangent t. And I'm just using different variables just so you guys don't always have to use theta or x or whatever. So here I have two expressions. I know that my goal is to turn it into a single expression. So I need to fuse these things together somehow. I'm going to use the strategy in my head of using only sines and cosines. So I already have cosine and sine. This tangent, I'm going to rewrite using sines and cosines. So this is equivalent to cosine of t plus the sine of t times the sine of t over the cosine of t. And now the sine of t times sine t over cosine of t. This sine of t really just means sine of t over 1. So I'm going to just multiply those things together. Cosine t stays the way it is, but now I have sine squared of t over cosine of t. Again, the single sine just has a denominator of 1. So 1 times cosine is still just cosine. Now, adding two things together, if my goal is to get one thing, I know from middle school math that adding fractions together means getting a common denominator. So I'm going to get a common denominator now. This cosine of t on its own, if I want cosine of t as its denominator, I'd have to multiply top and bottom by cosine of t. I still have the addition of that other fraction. Oops. Now I'm going to multiply here. Cosine times cosine is cosine squared. Cosine times the 1 that I didn't need to write on the denominator of that single cosine is just cosine. Second fraction is the way it was. Now that I have a common denominator, I can add these two fractions together. So cosine squared of t plus sine squared of t all over that denominator. What am I going to do next? Here's where I'll ask the audience. What makes sense to do next?
Have the primary Pythagorean.
Yep, use the Pythagorean identities. So go ahead, Jorlise.
It will equal to 1. The numerator will equal to 1.
Yep, and then 1 over cosine t. What does that equal to? Secant of t. And that's what we're trying to prove, so our proof is done. All right, so that was running through all 5 homework problems. Anyone have any general questions? Or need me to go back to a certain page? Jorlise, can you mute your mic?
Yeah.
All right, so if people have questions, obviously shout in or chat. I'll wait in the room a little bit longer, but basically what I'll do is I'll post this recording. I'm hoping it recorded. And then I'll probably send you guys some more practice for the weekend and into the beginning of next week. So look out for an email from me where I'll also include the link to the recording. So for right now, just review kind of what we did. If you had a different proof and it worked out, great, that's good. Just because it didn't match mine doesn't mean that it wasn't valid. If you want to send it to me and you're not sure if you did something wrong, you can email me pictures or whatever you need to do. Otherwise, look out for that email from me, and I guess have a good weekend. And I'm glad you guys were able to come. Don't forget, at 3 o'clock, your advisors are all having advisories, so hopefully they sent you a link already. If they didn't, they probably will. So that's at 3 o'clock. Okay? So thanks again, everyone, and I'm going to stop the recording and mute myself.
However, because we want you to get to know your
Bye.